So one of my favorite things about presenting at Rogue Worlds is the fact that now by the end of the second day, I don't really even need to give my talk. Pretty much everything that I was going to say has been covered by somebody else already in the audience. So I'll run through the slides, and forgive me if some of them are repetitious. I think I will still add a little bit of content in there for you. But I'm going to talk about free-floating planets in the era of Roman. So I usually open up by saying, okay, look, we have this beautiful plot here made by Matthew Penny, showing the discovery potential for Roman. We just heard a lot about Roman, and so to sort of remind you, we are on track for a September 2026 launch, 10 months from now. One of its core community surveys is going to be a 5-year microlensing search of the galactic bulge, the first space-based microlensing survey. It's going to have unprecedented sensitivity, thousands of planets on sort of intermediate semi-major axes, including analogs of all solar system planets with the exception of Mercury. So that's all fantastic, and I can only reaffirm everything Scott said. However, I have an issue with this plot that is different from Ruth's issue with this plot. Ruth wants to go up towards higher masses. I want to go further that way. I don't love the fact that this arbitrarily cuts off at 100 when the sensitivity of Roman extends all the way out to infinity. And so perhaps unsurprisingly, given that this is the Rogue Worlds conference, I'm very interested in what is out there. And there's sort of a reason that often it's not shown, and that is because in some sense, and I'm preaching to the choir here, but it is this sort of enigmatic terra incognita of planetary demographics, right? That being said, thanks to the extensive work that's been done by ground-based observations, we do have these sort of first initial hints of microlensing events out there at these low mass objects. And what are these things? Well, no surprise there, free-floating planets. We've heard that enough so far. And what I think is most remarkable, and this has been shown multiple times before, is the fact that these initial observations point towards something pretty impressive, which would be that there are actually something like 21 free-floating planets above the mass of Mars if you were to follow the Sumi power law there. That means that they significantly outpopulate their bound counterparts, and in some sense constitute the largest demographic of exoplanet in the galaxy. Like I said, preaching to the choir here, but this is usually how I drum up a lot of interest, and people sit up at this point and say, what? There are so many of these? So, okay, this is all very exciting. However, we only have a couple of events right now. That will change with Roman. With Roman, we will finally be able to peg down where this population comes from and start performing legitimate demographics of these unbound worlds. So my research really focuses on two questions. One is what might be out there? So what should Roman even be expecting to see on sort of the theoretical side? And then on the other side, what are we actually going to be able to see? And what are we going to be able to learn from Roman's data? So to begin with what might be out there, well, we can talk a little bit about the origins of free-floating planets. There have been some fantastic talks already throughout this conference addressing pretty much all of these. And it thrills me that I am maybe the third or fourth person to show something like this, where you say, all right, there are multiple different formation pathways. Maybe it forms like a star. Maybe it forms like a planet. If it forms like a star, you have these things like direct collapse that we've discussed. We've talked a lot about gravitational instability earlier in the day. And then if it's a more planet-like formation, you can have ejection via either planet-star interactions, or you can have it via planet-planet scattering. And again, we've heard a lot about these different things, and we had a really wonderful sort of review talk on this by Melina as well. So what's interesting, though, to me, and I think motivates a lot of the work that I've been doing, is the fact that each of these different formation pathways imprints something different on your final FFP mass function. So for direct collapse, you're going to make these high mass objects sort of at the very, very tail end of the stellar mass function. And you're going to be making them at fairly low velocities with respect to the stars. Planet-star interactions, on the other hand, are very violent. You can eject things very rapidly. And because of all the angular momentum stored in that binary, you can eject intermediate mass planets pretty efficiently. And then planet-planet interactions, this is really going to be best for low mass planets because you need a heavier mass planet to kick it out. And this will be kicked out at sort of intermediate velocities. So you can already start to think that if you start plotting this on velocity and mass parameter space, you sort of cluster into different areas. And that if we were to measure all of this, bless you, then by looking at the relative contributions in each of these parts of parameter space, you would get some sort of idea as to where these things are coming from. Now, granted, this is just a cartoon that I made in PowerPoint. And so if you really want to do this in a quantitative sense, you have to do some sort of population synthesis, some sort of attempt to build a free-floating planet mass function. And so this was the motivation for a project that me and Gavin Coleman, my collaborator, did, where we looked at simulations that he had run of these systems that start from just a gas and dust disk and evolve and slowly form planets, all in the core accretion, mind you, paradigm, and then evolve. And what we did is we ran this for a variety of different kinds of stellar architectures and types, various multiplicities, so a lot of binary as well as single star systems. And then we marginalized over all of these to ask, okay, given the distribution of these different kinds of systems in the galaxy, what at the end of the day would you get as your free-floating planet mass function? And the goal here with this project was really to see if there are any sort of interesting discernible features that you can then tether to underlying planet formation theory. So in terms of how this actually does in comparison to, for example, Sumi's results, it, much to both of our surprise, is actually reasonably not bad, given that we didn't tune it to try to match onto that power law. This was instead fit to the bound planets. And then we asked, okay, well, what do the free-floating planets look like? And within the error bars, it actually sort of matches on. It's a little bit low. And maybe that gap can get filled with other processes that we've heard about. But what you'll see here is I've cut it off sort of where we have the most sensitivity right now from ground-based observations. And below this is where we really enter that terra incognita. Interestingly, that's also exactly where we predict a pretty significant departure from just a naive power law extrapolation. And so this provides sort of a nice testable prediction for Roman to go after. Because if you see some sort of departure like that, there's some sort of interesting physics that's going on. And the nice part, too, is, well, again, this plot was already shown, so thank you for that. But because we tried to start as close to sort of ground principles as possible, you can actually tether these features to different aspects of planet formation. So in this case, for example, that strong non-monotonic feature is related to the fact that in binary systems, in tight binary systems, when the planet reaches a pebble isolation mass, it can rapidly migrate inwards towards the zone of instability where it gets kicked right on out. And so you see this peak around the pebble isolation mass just from that efficient migration that's occurring. And again, given the fact that binary systems have a lot of angular momentum with which to kick stuff, this actually ends up being a very dominant process for at least this model. So that's really neat. And so the takeaway here is that, is this the free-floating planet mass function in the galaxy? Well, I don't know. Maybe not. Maybe there's other stuff in there as well. But what it does show you is that free-floating planets can provide a very unique probe of planetary formation and system evolution, especially in the early stages that are observationally otherwise very challenging to probe. So that's Awesome. If we could see that, that would be really cool. But the question is, can we actually see that? And the answer is, well, we've already heard a lot about microlensing, and I won't dwell on this for too long, but there is a bit of a catch when it comes to microlensing, and that's the fact that you don't actually get direct mass measurements, right? What you get is sort of a degenerate combination of the mass, the distance of the lens, and the velocity of the lens, because all you're really measuring is the Einstein crossing time, right? This time scale of the light curve. So, okay, that means that on an event-by-event level, it's fairly challenging, actually, to pull out a mass. But there are solutions to this, and we've actually heard about both approaches already, so I will cover them very briefly here. The first one is, well, if you think about just the systems of equations, you have a bunch of variables, right? And if you can get more observables, right, you can solve that systems of equation and try to break all of these degeneracies, okay? So the first thing that we have is this time scale, and you get that automatically. That's true for any of the events that we're going to get. What's the next thing we can do? Well, you can also pull out finite source effects, which have been brought up as well. This basically just causes your light curve to look a little bit different, a little bit more rounded, because now the size of the Einstein radius on the sky is comparable to the angular diameter of the source itself, and so you get sort of this this feature. And by measuring that, you can get a measurement of theta e. So that breaks one degeneracy, which is getting you closer, but not all the way there. If you want to break the last degeneracy here, you really need this kind of parallax measurement. And we've already heard from Etienne why Euclid should be able to do this. There's a lot of other proposals to try to do this as well. But it's very important, right? And this is the hardest one because it's hard enough to find a microlensing event with one telescope, making sure you have two pointing at it at the same time in order to get this parallax measurement is doubly challenging. And so, we're campaigning hard to try to get these measurements, but they cannot be ensured, right? So we don't know that we will actually be able to do that. It's great if we can. That means that on an event level, we can actually pull out these things, but we can't be sure we're going to pull it off, right? So the other approach would be to say, well, Roman's going to provide us for the first time with the opportunity to do legitimate statistical analysis of this population. Right now, we don't quite have enough events to do that in a very robust manner. But with Roman, we're going to have population level statistics. And so because of that, you can basically treat this as like an inference problem, where given the data that we're going to collect, what mass function would best fit that? And there are things that have to go into that, obviously. You need galactic model, et cetera, et cetera. And so it's not quite as clean as if you can just break all those degeneracies and get the mass function. But at the same time, it is a well-defined problem that only gets easier the more data that we have. So fine, the TLDR on that is, in principle, Roman should have enough statistics to be able to sort of discriminate between these different hypotheses. But what I want to say is that while this is true, parallax will always help, even if it is only even if it's only for a couple of events, because this will help tether these things a lot better and provide us a much more rigorous and robust reconstruction of the mass function. And if we have the mass function, then we can actually start testing all of these fun planet formation hypotheses. So the takeaway here is that by leveraging both joint observations and population level statistics, Roman will start answering pretty fundamental questions about the demographics of these free-floating worlds. Okay, so that's sort of the summary. And the question is, what's next? Well, I'm currently chairing the free-floating planet working group for Roman, which means that we have 10 months until launch. And free-floating planets, as we've already heard, are going to be some of the first things that start cropping up in data. So a lot of my effort right now revolves around actually making sure we have an FFP detection pipeline ready to go, such that we can start doing science as soon as the first season. And so there's a lot that goes into that. I'm happy to talk about any of it at any point with anyone, and especially if they want to help. Yeah, at the end of the day, we are hoping to have this all ready to go such that we can start making some initial discoveries of free-floating planets pretty much as soon as possible when Roman launches. And so with that, I also am just going to say, perhaps this is premature, right? But in 12 months from now, Roman will have been up for 2 months, and potentially, there could be motivation for some kind of Rogue Worlds 3 if there are any brave individuals who might want to volunteer for that. Let me know. And with that, I'll conclude and say thank you.
Thank you, Will. We have plenty of time for questions.
You mentioned that by observing free-floating planets, there is a way to go back a few slides. I lost train of my thought. Go back a few slides. Go back. Yeah. Go back. Yeah. Keep going. Keep going. Yeah. You're getting to. Yeah. Keep going back. Yeah. Yeah. Keep going. I will stop you. Yeah, right there, right there. Okay, go forward. Right there. Okay. So connection between the underlying theory and you're saying that by detecting the free floating planets, we can say what theory. I've been doing this damn thing for 30 years. So please enlighten me. If you find the mass of a piece of rock in a space, how can you say what theory, what model formed that?
So I think you need more than one piece of rock in space is the takeaway here, is that if you can reconstruct the mass function of all of these free-floating planets, right, and you see some interesting distributions such like this, then it would already provide a hint for you that perhaps, circumbinaries are a dominant progenitor of these worlds.
We can, let's discuss this tomorrow at the time of the discussion. These are all misleading comments. There is no way that you can look at an object or a distribution of mass of an object and say how it was formed, where did it come from, when you don't know what its origin is. So I'm sorry. No, the answer is no. I've been hearing this for 2.5 days. I was trying to bite my tongue and not say anything, but no, you can't. You can't. Let's talk this tomorrow during the discussion session. But that is something that I want to mention. Anyhow, let's leave that for tomorrow.
Any other questions? Okay, we can thank Will.